All right, so I want to talk a little bit about the fossil record. So what you want to be aware of is the fossil record is a very good source of information for life on the planet, but it also has a lot of holes. So let's go through how we get fossils, and not a heck of a lot of detail, but probably the best place to get them is sedimentary rock. Sedimentary rock is where you have layers and layers that are laid down. And then if you have something that's living and it dies and it gets covered very quickly, then it will get fossilized well. Now, the problem with that is that there are certain other types of rocks that organisms may live in that do not fossilize as well. So it means we'll have abundance of information on things that live in the sedimentary rock area, and maybe not so much in other areas. The other thing that fossilizes well are hard parts, bones, teeth, spores and plants, seeds. So we have lots of records of those shells. I have lots of records of those organisms. Now the problem is soft-bodied organisms don't fossilize as well. So again, we are probably underrepresented in those cases. So worms do not have necessarily a hard component, so that makes it a little bit more difficult to get those. So next we have minerals being replaced by organic material. So on the left, that is a petrified wood. So there really is no organic material left. But it does give us great information on structure. You can see the rings, and you can figure out how old this thing is by counting the rings. And the width of the ring will tell you what kind of year it lived in. So there's lots of information to be had, although the organic material is completely gone. Sometimes we get lucky and the organic material is still there, like this leaf that was buried. Not only do we get the leaf shape and its structure and some of the organic material, but you can also see some of the scars on some of the diseases it might have had, or the organisms that were feeding on it. Then we have casts, where the animal is completely gone, but it's on the left-hand side. You can see at least the external features on the animals and what they look like. Unfortunately, what that might mean, though, is we might not have good information on the insides, the digestive system, those kinds of things, but definitely some information. And on the right, we have trace fossils. And this is a very famous fossil rock, and we see dinosaurs footprints. And the cool thing about this is you actually can get some behavior off this. You can see how fast they walked. Actually, you can see that there are younger ones next to it. And we realize the dinosaurs traveled pretty much like the large mammals do in the plains of Africa. Typically, the larger animals are on the outside with the young actually in the middle for protection, it is assumed. And then if you get very, very lucky, you might even end up with an entire organism. On the left, we have a type of fly that got stuck in sap and amber. And if you've watched Jurassic Park, that's supposedly where they got the dino DNA. And on the right is a not too long ago found a wolf pup frozen in the soil and very well preserved, 50,000 years old. So lots of different ways of getting this information. So again, great information, but just a reminder that it may lack some information depending on the organisms and where it is. And there's a way of dating fossils, and we're not going to do any problems like this, but realize that certain radioactive isotopes like carbon-14, uranium-235 have a half-life. And so you have your original sample, and it's going to have a certain radioactive isotope in comparison with the normal isotopes. And as you pull that away, what happens is the normal isotopes stay, but the radioactive isotopes will decay, and that decay is known, and it's called a half-life. So for carbon, the half-life is 5,730 years. So if I have a rock with 10% of carbon-14 in it, the idea is 5,730 years from now, I will have one that has only 5% because half of that would be gone. And then, so carbon is actually a good data for things that are younger, and I use that term loosely. And uranium-238 has a half-life of 4.5 billion years, so that obviously can be used on things that are older. There's also relative dating, and this is not, going to your family reunion and fighting your first cousin. This is actually looking at the layers when you're digging down. The assumption is obviously the stuff that is on the bottom is the oldest, and the stuff on top is obviously newer. And so we can get a relative age just by how things are sitting in the sediments. We know that there are problems with this because sediments are not laid down evenly over the years. And then also there is some places where actually the Earth has actually flipped over due to geological processes. So you want to be careful with this, but if you have relative dates and then you have some solid dates by absolute dating, you get pretty close to where things are. So I want you to realize how the fossil record can be used.